For this problem, we are drawing the Lewis structure for a particular ion, and then as we make more of these structures, we'll be indicating the formal charges, and then we're actually going to draw everything out into a larger orbital-based scale. And the reason that we're going to do this is we're going to identify specific orbitals that are used to make these bonds. So the ion that we'll be working with is the cyanate ion. So of course, whenever we want to draw the Lewis structures, break out every atom and figure out what your number of electrons will be. So oxygen has 6 electrons, carbon has 4, nitrogen has 5, and since we have a -1 charge, we're going to add in 1 more electron, which means you have a total of 16 electrons to work with. Now, of course, we need to determine now what our central atom will be, which will be carbon because it is the least electronegative. So carbon goes in the middle and will bond with an oxygen and bond with the nitrogen, losing 4 electrons to the bonds, leaving me with 12 electrons remaining. And now I start to fill up my terminal atoms based on the most electronegative first, which will be oxygen. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now all of my electrons have been used, which bodes a tiny little problem for us, which, as you can see, carbon does not have a full octet. So this is why we need to determine what the formal charges are, because with formal charges, it'll determine what the best way to make the double bonds will be. Now, I just want to remind everybody that this is still a -1 charge. So whenever you draw Lewis structures for ions, it's always nice to have a bracket with the charge on it so you constantly remember the total charge. So we're going to start doing the formal charge calculation. So the first one I want to do is carbon. It has a valence number of 4, but it has no outer electrons that are bonded, that are paired, I mean, and it has 4 bonded electrons, or the same thing as saying it just has 2 bonds. So I'm going to have 4 minus 2, which is a +2 charge. For me, I'm going to put 2 positive signs here just to let me know that that's what the formal charge is going to be. The next one I'm going to look at is going to be oxygen. Has a valence number of 6. It has 6 surrounding paired electrons, and it has 1 bond. So I have a formal charge of -1 on the oxygen, making that a negative there. And for my nitrogen, I have I'm going to just put that here. I have a valence number of 5. I have 6 surrounding electrons and 1 positive and 1 bond, which means I have a positive. Oh, sorry, I lied. I have a -2 charge here, so I'm just going to put 2 negatives on my nitrogen. Now, we want to create double bonds with this, but we have to start it from the least electronegative element besides the central atom. So between oxygen and nitrogen, since oxygen is more electronegative, it's not going to want to give up its electrons. So what we're going to do is we're going to take a pair of electrons from nitrogen and we're going to donate it. And anytime that you donate a pair of electrons into a double bond, you're actually going to negate 2 formal charges. So a positive charge on the carbon will negate with a negative charge on nitrogen. But if I was to redraw this in this new form, oxygen single bonded with carbon, double bonded with nitrogen with 2 lone pairs. Oxygen has its 3 lone pairs. I still have to deal with the fact that nitrogen is still negative, carbon is still a formal charge of positive because I just negated 1 positive charge, and nitrogen is still negative. So from here, we've got to determine, well, where's the next double bond, or where's the next pair of electrons going to come from? No matter what, oxygen is still more electronegative. So we're going to take another pair of electrons from nitrogen and bring that into the double bond, which means that I have an oxygen of a -1 charge. I have a carbon that's now neutral. I have a triple bond with nitrogen, and the nitrogen is now neutral. And that 1 negative charge on the 1 negative formal charge on oxygen is actually the total charge of the compound now. So what we've done is we've limited the number of formal charges, as you should, to get the best drawn structure. But remember, you're always pulling in electrons from the least electronegative terminal atom to make these double or triple bonds. So this is the formal structure, the best Lewis structure that we can have with this. Formal charges have been denoted as a negative, a neutral carbon, and a neutral nitrogen. Now we can start getting some information about this ion. So I redrew the structure here, and now I can go through and break up the hybridization and the orbitals present on each. So I'm going to start with the central atom because we know how to work with hybridizing central atoms. I have two electron domains. I have two electron domains on carbon. So having two electron domains on carbon means my hybridization is sp. On my nitrogen, I also have two electron domains, which is also an sp orbital. And for oxygen, I have four electron domains, which is an sp3 orbital. So when I go through and say, okay, I know my hybridization, so what orbitals are present? Well, for oxygen, we have 4 times an sp3 orbitals. With the carbon and nitrogen, this is going to be a little tricky now because I still have an sp orbital, but it's not all sp now. I have p orbitals that were not hybridized. So for an sp orbital, I should have a two p orbitals, and I should have 2 sp orbitals. So I still have 4 orbitals. It's just that 2 of them are hybrid and 2 of them are non-hybrid. And the same is going to be said for my nitrogen. I have 2 p orbitals, and I will have 2 sp orbitals. And when I go through for my bonded atoms, I'm now going to look at the bond between the oxygen and the carbon, which is a single bond, which means I have 1 sigma, I have no pi bonds, so that means that my bond order is 1 plus 0, or 1. For my carbon-nitrogen, it is a carbon triple bonded with nitrogen. I will always have 1 single sigma, but now I have 2 pi bonds, which means I have a bond order of 3. So my 2 pi bonds are going to come from the 2 p orbitals that are present. And the 1 sigma bond is going to come from the hybridized overlapping. So I know what my hybridizations are. I know the orbitals that are present. I also know how many of each type of bond I'm going to be making. This is enough information for me to draw the hybridization and orbitals present. So the next part of that question is to now sketch all the orbitals. This is going to take some space and also some imagination. So bear with me for 1 second. I'm going to first start with carbon because it is the most central atom. The way that we want to try to denote the orbitals is that for an sp, you want to try to shoot for the best teardrop that you can make, while for a 2p orbital, you want to just go for just a long oval. They might seem like the same, but this is about practice. This is making sure that we're as good as we can with practicing this. So as I said on carbon, we have 2 p orbitals, and we have 2 p orbitals and 2 sp orbitals. Now, since I know carbon and nitrogen are going to make a sigma bond, I will have a teardrop from carbon overlap with a teardrop from nitrogen. So that's one of my SPs used. And since I know that a carbon and an oxygen are going to be made with a sigma bond, that's going to be 2 other teardrops that are going to be made. So I've made my teardrops as best as I could. Now, if we recall what I said about carbon, carbon had 2 sp orbitals and 2 p orbitals. So my sp orbitals on carbon have now been drawn. So now I have to make my 2 p orbitals. Now there are 2 types to work with here. We're going to do a vertical. One, which I'm going to try my best to make as an oval. So now you have to remember that p is actually going to be vertical, like straight up and down, like an axial bond. So this up and down is a 2p orbital, which I'm going to call a 2p y orbital. And then I'm going to need to make another one for x. So I have an oval here, and then an oval going on the outside of the board, which I'm going to call 2px. And like I said, this is going to require some imagination. So that x is going to go into the board and out of the board. The py is going to go straight up and down. So my 2 p orbitals for carbon have been drawn, and my 2 sp orbitals for my carbon have been drawn. I'm now going to go to nitrogen, because nitrogen had a very similar setup. So nitrogen is going to get another teardrop. It's going to get 2 ovals, one going straight up and down, and another one going out of the board and into the board. And just for consistency, I'm going to write down SP, SP, 2PY, 2px, 2py, 2px, and that should be 2py. For oxygen, we have sp3 orbitals now. So I'm going to draw teardrops on three more teardrops on my oxygen. One going sideways, one going out of the board, and then one going into the board. So we have sp3 on our oxygens. So this is how all the orbitals are going to overlap. Now I'm going to put a pair of electrons in the sp overlaps and the sp overlaps there. I'm now going to draw my p orbitals. Now the p orbital, the p bonds, the pi bonds, are going to be when a particular type of p orbital overlaps with itself. So the py from carbon will overlap with the py from the nitrogen, and a pair of electrons are going to be right there in that overlap. So a py and a py are going to come together to form that pi bond. So I'm going to take the px from carbon and the px from nitrogen. I'm also going to get that overlap as well. So this is where my pi orbitals or my pi bonds are going to be made. So notice that I have one pair, two pair, three pairs of electrons within that same region where I have an overlapping of hybrid orbitals and p orbitals. I have a pair of electrons that are in an sp orbital on nitrogen because I have that lone pair that's not bonded. And then for oxygen, I'll have three sets of electrons that are going to be sitting outside these, that are going to be sitting in those sp3 orbitals. So just to double check everything, as I mentioned, we should have 16 total electrons in here. So I have 2, 4, 6, 8, 10, 12, 14, 16 electrons. So all of my electrons have been accounted for. And like I said, this is going to take a little bit of imagination. So ahead of time, I actually went and redrew this in color. So for those of you who are colorblind, I'm very sorry. However, I'm hoping that this newer image is going to be a little bit clearer as far as the way that I've delineated the hybrid orbitals. So if you can see here, I've redrawn them. I've kept the labeling the same, but what I try to do is I try to keep the hybrid orbitals a separate color from the 2px and a separate color from the 2py. But no matter what, I still have all of my orbitals with the electrons inside of them. And now I need to go through and to describe how each orbital is generated. So I have four types of bonds to work with. I have a sigma bond from my oxygen to carbon. The orbital on the oxygen is an sp3 orbital that's overlapping with the sp orbital from carbon and nothing from nitrogen. So when I ask you, when I state, I would like for you to describe the sigma bond, all it's really saying is which hybrid orbital from oxygen is overlapping with a hybrid orbital from carbon. I'm going to redo this now. The sigma is now for carbon nitrogen. So I'm going to have an sp orbital from, oh, that's a lie. I'm going to have an sp orbital from carbon, nothing from oxygen, and an sp orbital from nitrogen. And then the last remaining are going to be my p orbitals, my pi bonds from my carbon-nitrogen bond. So I have two of those. So again, nothing from my oxygens. The orbital for carbon is going to be a 2px overlapping with a 2px from nitrogen, and a 2py overlapping with a 2py on my nitrogen. Now, it's not always going to be x and y. If you chose to do y and z or x and z, that's completely fine as well, because you want to have that level of three-dimensionality. So let me just mention that if you chose to do a 2py and 2pz, that's acceptable, and a 2px and a 2pz is also acceptable as well. Because there are three types of p orbitals. There's a px, a py, and pz. So any combination of the two will work here. But like I said, when you go through and drawing these, imagination is very important, because sometimes drawing them out can be a little bit difficult to do. But this also helps you explain, when I talk about what a sigma bond is, what is that particularly, and with a pi bond, what is that as well.